Welcome to solverfy.
.84, we have 1 milligram of radium-226. This has a half-life of 1600 years for decaying into radon-222, which then has a much shorter half-life of about 4 days, where it decays by an alpha emission. And so if you go on with this longer than, considerably longer than the half-life of the radon, which doesn't take very long, comparatively speaking, because this is a huge difference in half-lives, the decay rate that the radon can have becomes limited to the decay rate of the radium, because the radon basically decays as soon as it's produced compared to the rate at which the radium is decaying. And so if it can only decay when it's produced, then the fact that it would, you'd only have a very small amount with this half-life producing the activity, and so the activity matches the radium more or less, and then this is basically constant. So under this limiting condition, we want to know, first of all, what is the activity of the radium? This is lambda times n. We know that this is the natural log of 2 over the half-life and then the number of bits of it. And so then this is log 2 over the half-life, which we need to convert to seconds. Times 0.001 grams times Avogadro's constant divided by the molar mass, which is 226 grams per mole. So this will give us the total number of radon atoms we have, which is what we want, and then this is the decay constant. And so then the activity is 3.66 times 10 to the 7th becquerels for decays per second. Now, we were told already that the activity of the radon is going to match that of the radium under this case. So we have 3.66 times 10 to the 7th becquerels as well. Now we want to find what the mass of the radon is, which is going to be roughly constant, because sort of as soon as any radon decays, or the rate at which radon is accumulating is much slower than it's decaying, and so you're going to just have a sort of small constant amount of the radon. So then the mass of the radon is going to be the ratio of the half-life of radon to that of radium times the ratio of the molar masses times the total mass of radium, which is our 1 milligram, and because its decay is very slow, that's roughly constant. And so we we have a sort of persistent 6.42 nanograms of radon that's being replenished at the rate at which the radium is decaying and then decaying so that it stays constant.